all the time. It's not, it is. It's useful for many things, and to be honest with you guys, I hope that the class will actually be useful to you. But if you can find a better use of your time, I never call roll or anything like that. You guys are adults, you know what you're doing. If not, you'll flunk. No big deal. On Desire to Learn, I use Desire to Learn heavily. I try to link everything from there. Most of my resources are in different places, like I'll put the videos on YouTube or something like that, because why not? But I tend to link everything from D2L. Over there, I have my contact info. That's my email, okaram1@kennesaw.edu. As an alternate thing, orlando.karam@gmail.com. Don't send private stuff to my personal email, right? We have HIPAA. You guys, your grades and stuff should not be discussed in stuff other than Kennesaw, but I'll probably have that account forever. Whereas the Kennesaw one, I'll have it this semester. Probably every semester, but who knows? I'm an adjunct. By the way, yeah, there is my cell phone. Feel free to text. If I'm doing something else, I'll just ignore you. It's not a big deal. Use your judgment when calling, right? Because I tend to not ignore phone calls, and I may get mad at you. There is my Skype, just in case. We may even put other stuff, but let me actually edit this thing, maybe? Can I edit this thing? Yeah. To mention one other thing. I am an adjunct here. And work a 9 to 5-ish. I don't respond right? When I'm at work, I'm at work. When I'm here, and this is different work, but when I'm there, I tend to ignore all this stuff. So you can text me, you can email me, I'll just ignore them until I get out of work, and then I probably will reply. I try. Actually, it sucks. I'm teaching Monday, Wednesday from 5 to 6:30, and then from 6:30 to 8 or 9 or whenever, which means I will probably not respond on Mondays and Wednesdays, right? Because I'll go home and have a beer or something like that. But the other days I will respond. Usually, if you see me on Skype, it's because I'm on my computer. Feel free to contact me, right? Again, if you try to initiate a call, I may say no, right? But normally I'll say yes. I work 9 to 5, so if you see me at 1 a.m., it's my fault, right? Feel free to contact me. It's probably, right? That kind of stuff, right? If I'm hooked up on my computer at 1 a.m., it's probably a great time to talk. I don't do it too much, but yeah. I will try to answer to everything and be available any way I can. If you want to learn, I want to teach. This actually worked. There's the syllabus. The instructor info is on D2L, so people don't spam me. People outside of this class, feel free to spam me. No. From the course catalog, we course advanced topics in algorithms, including randomized algorithms, the compositions of graphs, dynamic programming, linear programming and reduction, NP-complete problems, approximation algorithms, and quantum algorithms. I think it's a lie but I may add 5 minutes so that it's not a lie. I don't think I'll talk about quantum algorithms because I have no clue whatsoever. And you can probably read faster than I can. You can Google better than I can. The prerequisite is coursework in data structures or CS 5040. Just so you know, I expect you to actually remember data structures. I don't care which class you took and when you took it, as long as you know that stuff. And I will, next week, we'll cover kind of a super fast review of data structures, kind of what I expect you guys to know. But I expect you to remember that stuff. What does that mean? If you took the class 15 years ago as an undergrad, go find that book, right? Read that kind of stuff. If you pass because God is great, then again, go review that material, right? I expect you to actually know this stuff. Our textbook is going to be Algorithm Design by Kleinberg and Tardus. It is probably obscenely expensive. It is probably legally available electronically. It is probably illegally available electronically, but I won't tell you that. It is a fairly good book. I strongly recommend you get it, but you're adults, you know what you're doing. Grading scale, 90 to 100 is an A, 80 to 89.99 is a B, and so on, right? The standard Americanish grading scale. And my plan, and this might change a little bit, but we'll have a midterm that will be worth 30%, assignments that will be worth 20%. I tend to do tons of small assignments, do almost every week, rather than 3 big assignments or something like that. I'm a glutton for punishment. I hate grading, but I do it. We will have a paper that you will present and do something more involved. And that will be 10%, and the final exam will be 40%, and hopefully that adds up to 100. Yes. And then we have the standard stuff, right? If you cheat, I will come down on you as hard as I can, right? Don't cheat. If you have a question about what is cheating, ask before. Even if you ask after, it's a lot less worse than actual cheating. You may get a 0 on the assignment, but it's not cheating, right? Passing somebody else's work as yours is cheating, and if I catch it, I will go down on you as hard as I can, because that's horrible, destroys everybody else's degrees. And so, important thing about assessments, there is no curve grading. If everybody gets an A, I'll be super happy, right? But you need to get a 90 to get an A. If everybody gets a C, I'll go have more beers, but I'll still give everybody a C, right? I get depressed and angry when I grade and my students do badly. I feel it as a personal failure, but still, if you get a C, you get a C. If you get an F, you get an F, right? We are grading you against a standard bar. It's not a curve. There is no incentive for you to screw up your body, right? The other way around. If you help everybody learn, that's good, and chances are that you will learn more. Your grad students, try to use kind of proper formal communication. I'm not a terribly formal person. If you send it to me on LeetSpeak, I'll probably answer. Not on LeetSpeak, because I don't do that. But I try to respond all emails within 48 hours, and you have my cell phone, so you can escalate the things if you need a quick response. Normally, I expect you to come and take the test whenever the tests are due, but if shift happens, then we'll figure it out. And yeah, you have a religious holiday, let me know and we'll figure it out. I normally set up the tests and things like that by asking you guys, hey, I'm planning to put it on there is no particular reason to put it one day versus the other. So we can move it. Normally, I ask, and the first time is kind of a vote, and then after that, moving it is unanimous or something like that. But we'll have. If you have a disability, I'll work for you any way I can. Just let me know. If I don't know, then there's nothing I can do. The schedule is a plan, it's not a contract. If I deviate from it, I probably will deviate from it severely. There'll be two proctored exams, a midterm and a final. Ideally, I expect you to come here. This is not an online class, so I do expect you to come here. Again, special circumstances require special stuff. But any questions?
Are your exams computer-based, or are you
No,
paper and pen?
paper and pen.
Okay.
For this class, it would probably not make a lot of sense to make them computer-based, although we'll have programming assignments. But I found computer-based exams tend to make the bimodal distribution even more. So people who know this stuff would probably get a 90 on a test because you missed something. They'll get 100 on a computer test. People who are iffy on this stuff, who might get a 70 on paper, will get 20 on a computer test. So I tend to not do computer tests. I haven't done it in ages, but and for this class it doesn't. This is a programming class, but it's not a programming class. Unless you really want, and then we can make it more programming. But did I put the other stuff? Please tell me I did. No, I didn't. Oh, I put it here. No questions? I did put my stuff. I am horrible. I'll link this. Why the heck are you guys taking this class? Because it's required to get that funny hat. Besides that, right? Why do you really want to learn this stuff? There are three things that hopefully you will get out of this class. First one, you will learn a bunch of standard algorithms, right? Why is that good? Because many times they are standard because they are standard problems. And so it's not normal. Chances are that 95% of your time you are sticking data into a database, right? CRUD applications, that's how we live. But once or twice a year, you will get into this stuff, right? I don't expect that a year after you finish this class, of course, for the final, you'll know that stuff, but a year after, you'll probably not remember that much other than the names and where to go find it, right? And where to go find it is gonna be very important, right? I would expect you to be able to come up with a sorting algorithm without thinking, right? But I would not expect you to be able to balance a binary tree or something like that without going to a textbook, right? And that's what reference materials are for. But so you will at least know a bunch of standard problems and the standard algorithms and know where to find stuff, right? One really cool thing about the book and the ideas that people have done is you'll become much better at solving programming problems. One big thing is that now you will have a catalog of 100 standard problems, right? That you can just say, oh, this is just like this, but with apples instead of oranges. And so I can go solve it because I know there is a standard algorithm for this. I'll just go find it and implement it. The other thing is we will see actual techniques for coming up with those solutions, right? And so again, once or twice a year, this class is going to be super important. The other thing actually is that by going one level up, you fixate the other knowledge on your brain. So this class will take you one level up from data structures. So you will actually remember all the data structure stuff, and it will seem like easy stuff, as opposed to that horrible class that gave you nightmares. And then the other thing that shouldn't be as important, but it is really, really important, right? This will help you tremendously with your job interviews, right? Job interviews for developers, they have these kinds of problems. And so actually going through these kinds of things will make you a lot better at those things. Let me switch my hat. Workforfabric.com, we are an Amazon subsidiary. We are hiring. If you're interested, we can talk throughout the semester or something like that. Our hiring process sucks. We do these kinds of things. But most of the big ones do the exact same kind of stuff. Anyway, so what about standard algorithms? Well, we will review all the basic data structures, right? Vectors or lists, trees, hash tables, all those kinds of things. We'll review the basic algorithms, and all that's next week. We'll go over that in a class or two, and you will remember. You have seen all of this stuff. Chances are that you have seen most of this stuff, but one or two of the topics you were asleep, or it was the last class, it wasn't on the exam, that kind of stuff. We will really learn about graphs and graph algorithms. I don't know how deep you got into data structures. Most of the time, the way I remember data structures classes, I haven't taught it in ages. You really do linear data structures, you really do vectors and lists, and you really understand that stuff. You do trees, you kind of sort of talk about one balancing thing. Maybe you do one balancing trees, either red, black, or ABL, or 2-3, or one of those guys, kind of in depth. And then you kind of talk a little bit about hash tables and talk a little bit about graphs. Is that correct? So we will probably go a little bit deeper into trees and hash tables, not that much. I expect that you'll be able to go read stuff on it on your own. But we will definitely get into graphs in depth. And we'll do hundreds of graph algorithms. We'll actually, hopefully, you'll get, graphs are like matrices. They're like, everything is a graph. So once you get into graphs, then every problem looks like a graph. They are a really cool hammer. So you can nail tons and tons of problems by looking at them as graphs. So we'll spend tons of time on graphs. And there is some more other stuff, flow, network flow, which are also graph algorithms, that's kind of more advanced, and at least kind of the idea of probabilistic algorithms. We will do tons of problem solving. I think that is kind of the most important aspect of this course. We will, in particular, see divide and conquer, greedy techniques, and dynamic programming, and how they are interrelated. And those are kind of like, oh, when I see a problem, go look at one of those, right? Chances are that you can start an algorithm like this, and hopefully you get there. And probably probabilistic should be another technique over there. And then they're useful for job interviews, right? Most of the job interviews for developers have 1 or 10 of these problems, right? Either, usually you have a super simple programming problem, and then 3 or 5 kind of whiteboard stuff of this kind of things. Who in here is working professionally as a dev? No, maybe. No, not yet.
Used to.
Used to? Did you have any of these interviews?
It was very light problems because I started as an intern before being a full dev.
Okay. Did you go through any of these kinds of interviews?
Not for the IT.
Oh, you're doing IT. It's okay. We do this. We do this at Amazon. Definitely, I went through this same kind of stuff at Amazon, at Microsoft. I know that Google, Facebook, all of the other guys do it. So it's a very good thing to have. I list a bunch of sites for practice problems. I'm gonna make it part of your task. I'm gonna be putting stuff. So you go find problems and tell me, hey, we can solve it like this. Any questions? Are you all excited about doing this class?
My question was more kind of specific, and if you're going to go over it later, you can stop me. But are we going to go over like exactly what language we should use and how we should put in our code submissions and stuff?
Not right now.
Okay.
I can tell you, I will use Java in all my examples. Why? Because there's no good reason, right? We could use C++ or something like that. I work 9 to 5 with Java and Groovy and Kotlin. So Java tends to kind of be the easiest thing to do. It has some horrible things that suck, but for the most part, yeah, it sort of works. So I can tell you that's what I'm going to use. As far as what you submit, there may be, I'm assuming that you all know Java reasonably well, right? That it's not going to be a terrible thing if I ask you to program something in Java. On the other hand, no, it's not a challenge, but I can probably understand and run anything you throw at me. Don't go do it in bfunc or something like that, but most of the regular programming languages, and so we can talk.
Is it okay if we, while working on our projects, have them in public GitHub repos, or do we have to put them in private?
I would really, really, really like you to do it in private GitHub repos because there may be other, depending on the project, right? There will be times where you're doing the exact same thing as everybody else, and if you put it in a public repo, tall fences make good neighbors. There is, of course, no problem whatsoever in you putting whatever you want publicly after the class is done. Just, yeah, and maybe some of these things would be an interesting blog post or something like that. And like for your paper, for example, maybe something that could very well go in a public repo because everybody's going to be doing something different. So. No questions? No more questions? Cool. By the way, I have a confession to make. Now, this is the first time that I'm teaching this class, at least for 10 years. So I'm going to religiously follow the book and the slides that come with the book, because that will make my life so much easier. It's not that I'm just reading the book ahead of you, probably, but I know this stuff, but in terms of how to teach this stuff, I'm going to go with the book for the most part, right? Maybe 2 years when I've taught this 3 times, then I'll have much of my own flavor, but I'll try to, for the most part, I'll be following the material in the book. And I'll be stealing these slides from somebody. It's actually not the book author, it's one of their colleagues at MIT or wherever they are. So, can I download this thingies? If there are no questions, let me go do this stuff from the book. And chapter 1 is kind of a deeper into one actually interesting problem, and then talks about another 5, kind of to give you an idea of algorithms, right? The example problem is the standard, or one of the standard matching problems. And in the context in which they won the Nobel Prize in economics, it was matching med school students to hospitals. In the US, it's one of the few things where we do it. Other places do this kind of stuff a lot more. In the US, we kind of, when you finish pre-med or whatever you finish and you apply to med school, you apply and then you say, I want to get admitted into these 10 places, and all the universities look at, or the hospitals or the whatever they are, look at your curriculum and say, I want this guy, this guy, this guy, this gal I don't want ever, this guy I want, right? And so it becomes, well, you want 10 places and 7 of those want you, so who do you go with, right? And there used to be kind of a non-organized process, and then these guys created a national registry so that you apply one time, you apply to the national registry instead of applying to 10 hospitals, and you just rank all the hospitals, they rank all the students, and they run this algorithm and say, you go there. So that is the idea. Given a set of preference among hospitals and med school students, design a self-reinforcing admissions process. What's the problem? That would work, right? As long as there is no hospital that want me that I prefer to the one that I get admitted to, right? So if I get assigned to Keystone Hospital, right? That's okay. They want me, I want them. Life is good, right? Except that if Johns Hopkins wants me and I want Johns Hopkins, right? Then that would be a problem because I would have an incentive to go there, right? To go figure out how to get to Johns Hopkins, right? So that is what is called an unstable pair. A hospital H and a student S form an unstable pair if H prefers S to at least one of its admitted students and S prefers H to the assigned hospital. We assume that hospitals will take more than one student. A stable assignment is an assignment with no unstable pairs, which is a natural and desirable condition because no side deals would make sense, right? There is no incentive for me to do that. So that is the stable matching problem, right? How can I do it? Given a set of n hospitals and a set of n students, how can I do it? Each hospital ranks students, each student ranks the hospitals, and here we're doing one student per hospital, and then we go try it, right? A matching is perfect if, and this is in general, that has nothing to do with hospital, this is just graph. The set of M, right? The size of H and the size of S is N, so we match one student to one hospital. Given a perfect matching M of one student to one hospital, we can find an unstable pair, right? And that's the same definition. Stable matching has no unstable pairs. How can I do it? Notice that, do we even know that a stable matching exists? No. In fact, if we modify the problem slightly, we make it the stable roommate problem. There is no guarantee of a stable matching, what's the difference between a stable roommate and a stable matching of hospitals, and what's the difference? With roommate, there's only one set, right, that I'm mapping in pairs, whereas with here I have hospitals and students, right? It turns out that with hospitals and students, right, where you have two disjoint sets, there is a stable matching always. And this algorithm guarantees to find it, right? It's Gale Shapley for the two guys or gals who invented it. I don't know, we use their last name, so I have no clue. So you initialize n to be the empty matching, has no matches, while there's a hospital H which is unmatched and hasn't proposed to every student. Let S be the first student on the list of H, to whom H has not yet proposed, the ones that they would prefer out of. If S is unmatched, we add the hospital student matching, right? So we match H to S. Now, if S is not unmatched, but it would prefer the hospital H to the current partner H prime, we will take out H prime matches to S with H matches to S, right? And if not, that is, the student is assigned to a hospital and it actually prefers that hospital, then S rejects H, and we keep going. So now we have one less thing to consider, right? And we keep going, and eventually we return a matching. Now, is this an algorithm? Does it terminate? Does it do the right thing? Well, it runs, it does stuff. Is it the right thing? Well, let's go write unit tests. No, we'll do math rather than unit tests. So given that hospitals propose to students in decreasing order of preference, right, and we are eliminating them, and that once a student is matched, the student can never go unmatched. It can only go up, right? At the most, right, the algorithm will terminate after n squared iterations, right? Basically, we analyze all the possible, right, hospitals with all the possible students. If we were really unlucky, right, every time we would be trading up. Does this make sense? So at most, right, each time through the while loop, a hospital proposes to a new student, and there are only n squared possible proposals. So at most, we'll go through n squared times. Yes, no, maybe? I see gears turning. Linda, you have a question.
Me?
No, she, no? Okay. Does this make sense? Cool. Now, is it correct, right? We have seen that it will produce a matching, right? And that it will terminate, and that's important. If your algorithm never terminates, it kind of sucks. So does it produce always a stable matching, right? And we normally do proofs by contradiction, because that's kind of the obvious most of the time. By contradiction, this we are going to first, let's see that all students get matched, right? All hospitals get matched. If there is a hospital that is not matched, then we should have, there needs to be necessarily a student that wasn't matched, because there is the same number of them, so we should have proposed, that hospital should have proposed to that student. So that couldn't happen, If a student was not matched, then that would mean that a hospital was not matched, and we just said that that can happen, right? Now, it produces stable stuff. Assume, or we will prove that there are no unstable pairs, right? Imagine that there is an unstable pair HS, right? Or actually for any pair HS, right? There is two possibilities. Either H never proposed to S in our algorithm, but by construction of the algorithm, it proposed to a student that it prefers, right? It cannot prefer S to S prime, whoever it is matched to. Or if it proposed to S, then we know that S projected H, and so S would not go to H. So we can never have an unstable pair. Does this idea make sense? This is the kind of stuff that we are going to be doing in this class, right? As far as mathematicians are concerned, this is an abomination. We are waving our hands, right? But as far as computer science is concerned, this is sort of kind of a proof, right? It's not a real proof, but we're going to be doing a lot of this kind of stuff, where, rather than formal proofs. You can actually go look at some of the original papers. They listed there. Let me go find the cool thing and then go back. These guys got the Nobel Prize in economics for this stuff, and it is almost the algorithm that is used for med students now. They have some additions, and also for matching organ donors to patients. So, okay. So how could we implement this in order of n squared, right? Hospitals and students would be represented by numbers, right? We will maintain a list of free hospitals in something like a stack or a queue. And two arrays, student of age and student, where I pass the student, I pass the hospital and it gets me the student that's matched, and hospital where I pass the student and it gets me the hospital. Right? I think this is reversed in my brain, but and we'll use 0 for the hospital is unmatched, or -1 or something like that, right? If you're for each hospital, we maintain a list of students ordered by preference, and we'll just be taking off the list, right? When and kind of a pointer of the next student on the list, right? So what we will do is create a list of a reverse list of preferences. This is the list of preferences, right? So what I'm going to do is reverse it. So instead of, since hospital 8 is the first one, I'm going to put 1 on 8. Does that make sense? So I put what's your place on the list. That's on the inverse, and that allows me to quickly determine whether you prefer this hospital or the other. Right? Producing that is order of n. I just have to go through the list once, right? It's order of n per student, so it's order of n squared. right? Now, one question is, there may be several stable matchings, and which one do we get, right? What's going to happen is, in this case, right, it could be Xavier and Yolanda are valid partners for Hospital Atlanta, the Hospital Boston, right? And so we kind of have not like a cycle, but like a cycle, love triangle between these people, right? And so who gets the one they prefer, right? Not among everything else, but in this case, Xavier prefers Atlanta to Chicago, right? And Yolanda also prefers Atlanta to Chicago, right? But Atlanta prefers Xavier to Yolanda, and Chicago also prefers Xavier to Yolanda. So who's going to be happy, right? Depending on the order in which we do the assignments, we either give preference to the hospitals or the students. And the way we did the algorithm, you will give preference to the hospital. So you get a hospital optimal assignment. So the hospital wins with our algorithm. Yeah. What happens to the students? They are slightly doomed, right? If they have 2 or 3 that they could prefer, they may not get their choice, right? It is actually pessimal for students because the hospitals get to win. Interesting thing. Given this, could it be beneficial for a student to lie? Yes, it could, right? Because it may allow them to actually get the hospital that they want because they're kind of reverse sorted in that case. So the hospital doesn't have any preference for lying because they're getting their optimal assignment, but the students may have it, which is just interesting, right? This algorithm is simple enough to be explained and probably to be implemented in a couple of hours, right? But of course, real life tends to suck and be a lot more complicated. And so there have been a bunch of extensions, including some participants say, I'm not going to that hospital ever, right? Or some hospitals say, I'm not taking these students ever. I'm not touching them with a 10-foot pole. Hospitals may have more than one position, and that's relatively easy. There's an unequal number of positions and students, and that's a kind of a hard problem to solve. But so we define slightly different definitions, and they actually have a bunch of other stuff. This is the U.S. National Resident Matching Program. I think there are similar programs in a bunch of other countries now, modeled after these. Started in 1952. They used a different algorithm. Then they started doing something like this, and they have a bunch of other constraints, like allow couples to match together, right? It would kind of suck if you get to a hospital in Chicago and your wife gets to a hospital in San Diego, right? And so, and these two guys got the Nobel Prize in economics for this. So, come up with your algorithm You may get a Nobel Prize. Okay. Bunch of similar things, right? Content delivery networks. We have a bunch of locations, edge locations, right? The user prefers the web server that provides the faster response time. The web server prefers to be cheap, right? Or a combination of those. And so how do you assign users to servers, right? This is kind of Netflix kind of stuff. And there is tons of papers. I hope and I will force you to read research papers. But I hope that you will do it for fun, in a weird, twisted sense of fun. It is actually a lot of fun to go read these things, right? Some other representative problems. Interval scheduling, having a set of jobs with start and finish times that compete for a resource, right? These are for a machine, for a person, for, right? Where the machine has to do this stuff, right? What's the maximum cardinality subset of mutually compatible jobs, right? Jobs that don't overlap. For example, if I do job A, I cannot do B or C or D or E or F, right? I could do A and G or B, E, and H, right? Or other things. And we could define different optimalities, like, well, I want the maximum, largest number of jobs, or the best use of the machine, or something like that, right? And we'll see actually how to solve these kinds of algorithms. Similar, but now with weights, right? And that would be either use of the machine or who is paying me more, right? So that's the same kind of stuff, different idea of what's optimal, what's best. My native language is Spanish, so I tend to mispronounce the things as if in Spanish. So I'll say bipartite matching. I'll probably mispronounce this horribly, and I have no clue what's the right pronunciation.
Bipartite?
Bipartite?
Yeah.
Cool. Then I'll try to call it bipartite and fail half the time. Given a bipartite graph, find a maximum cardinality matching, right? So find a matching with the most edges. That doesn't repeat, right? An independent set problem, right? And you can see these things. Well, this thing is not obvious, but we do have a graph, right? Who fights with whom, right? This is obviously a graph, right? You have nodes and edges, right? This is obviously a graph. You have nodes and edges. This is kind of a game, right? Given a graph with weights on each node, you select and you also kill the ones next to it, right? So like, if I select 15, you cannot choose this. And then you can go from the other, and so that's a cool game. Let's go implement it in Android. And you're trying to reach the maximum weight. So we will see that these are kind of related, that we are talking about finding sets of nodes or things in a graph. We'll see for interval scheduling, we have a greedy algorithm that works. And greedy algorithms is just choose the first thing that makes sense, right, and keep going. And we'll see exactly what's the greedy part in this case. And greedy algorithms are amazingly fast and amazingly simple. They tend to not work, right? But for many problems they work. For many problems they work and they give you the right answer. For some problems they don't officially work, but they're actually not terrible, right? If you think about how to get to a destination fastest, right? And avoid traffic, what can you do? If you have a bunch of different routes, right? You could say, oh, let me just go to the thing that has less traffic, right? It's not necessarily good. Maybe you have traffic later, right? Maybe you actually end up going back in loops, but at least you have less road rage, right? That's kind of the idea of greedy. Try, and many times it sort of kind of works, right? It's a very decent heuristic, even though it may not be perfect. For this problem, it's actually perfect. Dynamic programming is a really cool technique that we will hopefully understand. And that usually is pre-computing smaller solutions, right? If you think about divide and conquer, you make smaller problems, and then with dynamic programming, you save those solutions in a table. And rather than try it again, you can just go find it in the table. We'll see memoization, which is just making a dump table. And then usually dynamic programming ends up being an elegant way of building the table so that you don't use too much stuff. Bipartite matching, we'll see there is a horrible algorithm based on flow. Order of n to the k. What does this mean? We're doomed. The independent set problem is actually NP complete, which means we are really doomed. And then we'll see other definitions of doomed. For the most part, right? And we'll talk about this next class about O notation that you guys should be reasonably familiar with, but we'll really go over it. Depending on how fast your computer is and things like that, right? You can try to get a faster computer. At some point in time, if your n, the size of your input grows, right? It may grow, the solution may grow a lot faster than your computers, or the money for your faster computers, right? Normally, we can solve lower degree polynomials. N log n, n squared, we are good. N cubed starts becoming painful. Beyond n cubed is probably painful. Then there is NP complete, which means we know there is no polynomial algorithm. Well, actually, we believe that there is no polynomial algorithm, because if there is, then you have just solved a million really hard problems, and you'd get a Nobel Prize or two and become a billionaire. So we all assume that that's not going to happen. And p-space is a different classification where besides time also space is limited. And so we will, it is also important to know when you're doomed, right? What do you do if you have a problem and you have an algorithm that takes n squared? Implement the algorithm, right? Well, it's too big for my computer. What can I do? Get more computers, use Hadoop, use stuff like that, right? What about if it's n to the 25? I'm doomed. There is no Hadoop. There is no AWS that's going to save me, right? So what can I do? Well, and much worse is 2 to the n or something like that. Then I know that I'm doomed. for any kind of large value of n, and then I have to start looking at artificial intelligence and those kinds of things to find a solution that doesn't suck, right? So it is very important to recognize it as, no, you're never going to solve it perfectly, so try to find one that's good enough and that you can pay for. And we'll study some of those complexity classes. Any questions? Cool. Life is good, and I can give you back 6 minutes of your life. We will cover chapter 2 Wednesday, and I will also mention assignment 1. It's already there on the web.